All right, the next topic is kind of a grab bag. It's got some old stuff, some new stuff. We've got the arguments centered around alcohols and the types of oxygen atoms in alcohols, phenols, and thiols are sp3 hybridized oxygens or sulfurs, for example. So we're taking a structural approach to this next set of topics. So here's an oxygen atom in the center. It's got 4 sp3 hybrid orbitals around it. It's fully sp3 hybridized. 2 of them are forming bonds in this molecule. The other 2 are in lone pairs. Set up like this could be same for sulfur. Phenols have an aromatic ring with an OH attached. Thiols are like alcohols except with sulfur. Taking a look at some of the simple nomenclature of alcohols, we have these compounds: methanol, ethanol, which is a primary alcohol because the carbon bearing the OH group is connected to only one other carbon, so it's a primary carbon. In isopropanol, the carbon bearing the OH group is connected to 2 other carbons, so it's a secondary alcohol. Tert-butanol is a tertiary alcohol for the same reason. As you go in this direction, they're less reactive in many reaction scenarios. There's always exceptions. Some more simple nomenclature here on the right. If you have 2 alcohols, it's a diol. If you had 3, it would be a triol, and so forth. So this is 1, 2, 3, 4, 5. It's a pentane. It's 2,4-pentane diol. Here we have cyclopentanol. That's easy. Here we have 2-methylcyclopentanol. Note the numbering. Chemists don't have left to right directions always. We have things floating in space. So that's 2-methylcyclopentanol. 4-bromophenol, so we're calling this a phenol with a bromo group on it. Thiols have pretty different nomenclature. We call this ethane thiol, as if it was ethane alcohol. 4-methylcyclohexane thiol. 1, 2, 3, 4. So you just want to review enough nomenclature from the reading to be able to converse reasonably well. We could spend all quarter on nomenclature, and we don't want to do that. You can develop more nomenclature skills as you go along solving other problems. The reactive properties of sp3 hybridized oxygens and sulfurs and the like are similar because they're based on the structure. So the lone pairs on oxygen can form covalent bonds. Same with sulfur. That's one aspect of their reactive nature. OHs and SHs can be deprotonated in this way, producing a deprotonated form that's going to be more active in a lot of types of reactions. So deprotonating makes the oxygen or the sulfur more reactive, most likely. These atoms in their sp3 hybrid state can hydrogen bond. Actually, they can hydrogen bond in other states as well. But hydrogen bonding is a really commonly observed behavior of OHs and SHs, so forth. NHs too, for that matter. Centered around the discussion of the preparation of alcohols, we talk about how to make alcohols, but more importantly, we talk about new methods for making organic molecules. So some of this is review. The SN2 reaction can produce an alcohol in this way with an oxygen nucleophile coming in and kicking off the bromine leaving group. And you see the change due to inversion of stereochemistry. So this topic we've just covered. So clearly we can make alcohols via SN2 reaction. If you recall the end of first quarter, you can make alcohols by addition to alkenes in this way. So you could review this chemistry. You produce a carbocation after the bond-forming reaction of that hydrogen. Oxygen in water can come straight in and bond, creating that bond. Remember, bonds are just pairs of electrons being shared. Then a quick deprotonation, and we want to know that deprotonations can occur so easily like this that eventually we don't have to necessarily show it every time because it gets tedious. So that's also review addition to alkenes making alcohols. Now the new stuff, and what I meant in the above title at the beginning, the beyond, now we're away from some of the chemistry of oxygen as it was begun here. The general mechanism is that of a nucleophile attacking a carbonyl group, and it can do so from the top face or from underneath because we have the planarity, trigonal planar nature of a carbonyl group. There's also inductive effects as shown here. So there's a pull. A lot of organic reactions are a push and a pull. So these electrons are going to go up toward the more electronegative oxygen, giving you now an sp3 hybridized tetrahedral state. This is what would result from the underneath attack here. You would also have the equally likelihood above attack from above, followed by a quick protonation like I just mentioned. You get an alcohol plus whatever this nucleophile is, and if that molecule is chiral, you would have an equal mixture of R and S because of the likelihood of attack on top and bottom. Now you can define different kinds of nucleophiles, and we've got a whole bunch of types. We can continue on this topic sort of with oxygen and sulfur nucleophiles, and an example of nitrogen too. So the sulfur nucleophile attacks in this way to a carbonyl in exactly the same way, a quick protonation of the oxygen, and we get R and S configurations of this molecule with the nucleophile having added. Nitrogen can do very similar, attacking a carbonyl, pushing out electrons up on oxygen. If we add a proton to oxygen, and you can visualize the loss of a proton from the NH3 group, we end up with an OH and an NH2. So oxygen, sulfur, nitrogen nucleophiles. Now, hydrides, this is something entirely new, perhaps. So hydrides are delivered. They don't really exist in this form as an H-. Hydrogen can't really just float around as an anion. It's delivered from these hydrides as in the arrows, using the arrows you see here, these two electrons forming a bond and bringing the hydrogen with it, kicking those electrons up. Therefore, you have this new bond here, and then protonation can occur on this oxygen. And of course, you get your mixture of stereoisomers in this case. Lithium aluminum hydride, like sodium borohydride, acts in exactly the same way. So you could probably fill this area in exactly the same way. We already saw an example of a simple carbon nucleophile, the nitrile group, simply adding in this way, exactly the same mechanism, protonation of the resulting O-, you get S and R configuration, having added a carbon group. And you can actually do a lot more chemistry with a nitrile group that's been attached on there, because it's a reactive group, a C triple bond N group. So the next subject is going to be really our more desired subject, how to add larger and more complicated carbon groups to other carbons. The formation of carbon-carbon bonds. So critical for constructing organic molecules. And so there's really going to be a lot more interesting and more practice problems on this topic. It's given its importance. So there is some decent problems in McMurray, some decent problems in Klein. I'm not crazy about the reading in either of these, but it certainly won't hurt you to do the reading. You'll see how much of a jumble this subject